Now I think that there is a lot of things ready to be used. The problem is that the people does not know it. So I would suggest to a young scientist to try to stay on top of the bioprocessing, understanding what is needed, what are the problems that the industry needs to solve, and then understand everything which is around in terms of mathematical modeling, different processes, continuous, non-continuous, PATs, and the value today can come from the selection of the right sensor or develop a soft sensor based on some spectroscopic sensor connected to mathematical model using Kalman filters, for example, to combine model and experimental results.
Hey, smart biotech scientists, welcome back. We are in the middle of a conversation with Massimo Morbidelli on integrated continuous biomanufacturing, chromatography, and the future of recombinant protein manufacturing and machine learning-driven controls. We are honored to have Professor Massimo Morbidelli with us today. As a Professor Emeritus at ETH Zurich and Politecnico di Milano, and the co-founder of ChromaCon and DataHow, Massimo Morbidelli has been at the forefront of bioprocess innovation. He is currently the recipient of the ERC Advanced Grant Continuous Digitalisation of Bioprocesses at the Aristotle University of Thessaloniki. So in part 2 of our conversation, we are delving into the realms of integrated continuous biomanufacturing, cutting-edge chromatography techniques, and the future of recombinant protein manufacturing. And if you haven't listened to part 1 yet, please go back first. And now stay tuned for part 2. Are you juggling the complexities of CMC development while trying to enjoy the beauty of biotech? Have you ever wondered if there's a way to simplify bioprocessing? Welcome to the Smart Biotech Scientist podcast, where we're diving headfirst into the very challenges you face. We're breaking it down, demystifying the jargon, and giving you the keys to unlock your full potential. I'm your host, David Brohlman, and I get it. With 15 plus years in the biotech industry, I face the same challenges you do. There's a way to simplify and streamline so you can remove complexity, you can skip trials and errors, deliver without delay your groundbreaking therapy to clinics at market, and still enjoy every single step. Do you want to learn how industry experts and I did it? Grab a cup of coffee and your favorite notebook and pen. Now is the time to take your bioprocessing game to the next level. Let's smarten up biotech. Now I'm curious, Massimo, because, we have obviously a lot of learning we can transfer from the map space from Joe. There's a lot of work that has been done on that space. And I'm totally convinced, and many companies, including DataHow, have shown that you can significantly reduce the number of experiments just by transfer your learning. What challenges do you foresee as you're now addressing new modalities? Like, what learnings do you think cannot be transferred?
What learning cannot be transferred is a very hard question. So this is what we are trying to explore in the internal projects at DataHow, which is to find what are the actually, we are looking for what are the information that you can transfer, right? The idea there is that, of course, if you are in a situation like the one that I described before, which is the virus is changing the variants and then you change the vaccine, these things are going to be very similar. And there you transfer a lot. You can really decrease the number of experiments needed to design the new process by 80, 90%. Is incredible. But now when you start changing the cell line, the product and everything, then how much is that? I thought that, for example, if you try to go from a CHO cell to, let's say, some producing a monoclonal antibodies instead of producing a fusion protein, for example, I would expect not too much to be transferred. Instead, there is a lot. You can still decrease the number of experiments by at least 50% in that case. And even changing the cell line, it is significant in the order of 50%. Now, if you go from CHO to new modalities, this is a bit to be explored yet. But I've been surprised always in a positive sense for how much you can transfer. But in fact, if you take a guy who does not know anything about cultivations and ask him to do a new modality, or you take a guy who's an expert in CHO cell, obviously the second one is going to perform better, right? It's not, it doesn't come as a surprise. It's rather obvious. It's not the same one, but respect to nothing, zero knowledge is still a lot.
Absolutely. And I think also the technologies are still evolving and we'll probably see even much better results in the future. But before we dive into a bit more into the machine learning part, let's just focus also on the technology, on the chromatography itself real quickly, because you're developing continuous technologies. And what trends do you see in that space to make these unit operations more efficient? And these technologies help increase the efficiency of these integrated approaches?
So I think that there is some space still to develop stationary phases which are more efficient in the context of continuous operation. And so the classical trend of people developing stationary phases has always been having batch operation in mind. Now, what happens if you instead have continuous? So continuous means that we can have higher flow rates. So this means that we would like to have larger particles to decrease pressure drop. And so this idea to put smaller and smaller particles to get better mass transfer is not a good idea for continuous operation. But we can recover what we lose in terms of mass transfer by using the continuous or concurrent operation of the unit. So that there is something to be learned. And I see this monolith, for example, have some potential in this direction, or these chromatographic stationary phases which resemble membranes continuously more and more. So at the end, we'll probably have some material. We will be like, sometimes they call it chromatographic membranes. So something in this direction that could perfectly fit the capabilities or the characteristics of a continuous operation. But I have to say that besides this, I always thought to continuous operation advantages, talking about chromatography now, for example, MCLGP, applied to monoclonal antibody purifications. I always thought in terms of how much solvent we can save using continuous versus batch, how much we can increase the yield, how much we can increase the productivity. But I've seen applications of this technology now in Bachem by Ralph Eisenhut. For example, he gave wonderful talks about this. He has some in YouTube also that anybody can listen. The advantages, even when using these technologies for peptides or oligonucleotides, are very large. And in terms of, I've seen that he talks about increasing productivity by 10 times, decreasing the solvent consumption by 70%. So with the corresponding saving in sustainability of the process, as you can imagine, in the peptide areas, the solvents are something else and not just water. These advantages are still there, but what he shows in his investigations, which I found really amazing, is that the big advantages do not even come from there. The biggest one comes from the fact that now you're working 24 hours, 7 days a week, that you can leave the lab empty, go home, and the thing keeps on purifying and going. The number of advantages that we can get there, like smaller waste treatment facilities, for example, when it comes to waste treatment, the decrease in the personnel, because in a continuous operation, the number of analytics that you have to do is much less. So that requires less analytics, less time, less people to work on the unit. So at the end, the advantage of 10 times more productivity is, yes, is there, but is there in terms of having a smaller columns, having shorter times of operation, and then you work continuously across the clock. And this brings, very short occupation or very high occupation efficiency of the unit. So this, I think, is the big advantage. It's not only because of the more efficient process that we create with continuous concurrent operation, but it's because it's automatic, which is like,
because it's automatic and you can reduce costs and you have a smaller footprint. You can also reduce the risk of failure due to the high or very well performing PAT on top of that. There's a lot of benefits, right?
Correct. You mentioned the magic word, PAT. The progress that we have done in PAT these days is tremendous. So we have sensors based on spectroscopy, Raman, infrared, others, who give you a response in zero time. We can have really a machine learning tools which are applied only to the sensor, the spectroscopic sensor, in order to extract from the spectrum the maximum number of information. So we have seen, well, this was a collaboration with Merck, Serono, that David, you may happen to know where they are, what they do, right? You probably were still around at that time in there, I mean. So that from a Raman spectrum, you can measure the viable cells, you can measure glucose, you can measure ammonia, you can measure many things in one spectrum and online. And so you see, now having continuous operation becomes possible because if you have to take a sample, go to the analytical lab, make 1 week experiment, when you come back, the continuous operation is gone ballooning, right? You cannot do that. So PAT is a key in developing continuous operation.
Yes, absolutely. And now, with all these advancements in technology, how do you foresee machine learning and AI revolutionizing the landscape of bioprocessing?
Yeah. So what I think is that the basic concept is that when you go from lab scale reactors, maybe 1 liter, 2 liter, 5 liters pilot unit, and then thousands of liters commercial, the scale changes. Now, the digital twin has the same size. The model is the same. There is no scale up there. So what you have to learn is to start developing a digital twin at the very early stage so that when we go and decide to scale up to pilot, for example, we don't have only the experiments done on the laboratory batch reactor. We have also the digital twin developed to simulate and optimize online that batch reactor. And then when you go to the next scale, the digital twin is the same, the model part. And you change the big reactor. Okay, you change the scale. That requires some work, but the model you have already accounts for a lot of things which otherwise you have to account for in your mind. And this makes it very difficult. And some of these things that typically are non-scalable concepts, they are just going to be reproduced identical to themselves. And here comes also the concept I was telling you before. So I was telling you this transfer learning concept. You know how to design a process. Now a new molecule comes in. What can you use of the knowledge you created in developing the previous process to develop this new process? So these are transfer learning, which we say transfer across molecules, across process, because we transfer the learning from one process to the next process. But if you think about it, what we go for scale up that we did in our life in biotechnology all the way along, right? What we do is transfer knowledge across scales, from the laboratory scale to the pilot scale to the commercial scale. The process we do is the same, is transferring knowledge across processes when you go to one variant to the next one for a virus, for a vaccine against a virus, or across scales when we go from laboratory to pilot to commercial. So the incredible thing is that from a machine learning point of view, the techniques are the same techniques that you use in the two cases. When you're based on science, of course, these are different concepts, completely different ideas you have to use. This is really, I think, where we can change completely the view. So we will have to use this concept of digital twin starting from the very beginning of the process development and then move all the way to the manufacturing scale.
While this technology is game changing, what are the key challenges in integrating machine learning into the bioprocessing, and are there any solutions to overcome them?
Look, in terms of machine learning science per se, the algorithms are more or less what ready, say, to be used. There is a little thing that has to be changed, which is the one I mentioned before, which is that we are not doing big data. When you go to bioprocessing, we don't have big data. So the paradigm is inverse. So we have to minimize the number of data to achieve a goal, not to try to see what we can get out of a enormous amount of data because we don't have that anyway. And then integrating this into bioprocessing, this machine learning concepts into bioprocessing, I think that what has changed completely the world is the possibility to have sensors, because the advancement which has been made in the PATs in the last 10, 20 years are amazing. And this has been enabling really for the use of machine learning concept, at least in their online version, into manufacturing. And on the other hand, is the fact that we still have to understand the process. So while in other areas of machine learning, like I said before, image recognition, for example, or language translation, you don't need to understand nothing, right? You just use the statistics and this math all the way through. In our area, you still have to understand a bit what you're doing. And this is the key of the success of DataHow. The DataHow does not have computer scientists and bio people. They have everybody who is half computer science and half bio people, which you can achieve also by putting the two different guys working together. But this is a company which has in the focus bioprocessing. So with respect to much larger companies who could Google or others, they will never come to touch bioprocessing because that is too complicated for them. At least not in the near future.
Because we are not in big data. So we are in small data. And also what I would like to add is that bioprocessing data is extremely expensive. So I think we should further develop these technologies to reduce the number of experiments.
Yeah. And that means cost and time, which is, as you know, even more important for us.
So as these technologies will evolve further, can you give us some advice of how can we stay ahead of the curve? Because obviously change is happening so quickly. What strategies would you recommend?
This is a very difficult question. The answer is very different from academia and industry. So industry has to be very open, not to be scared, not to be afraid to bring people to approach different kind of knowledge into their teams. Of course, they have to think outsourcing or doing in-house. That's always a big problem. But anyway, they have to integrate computer science into their teams. In the biopharma industries, will have, if you wish, a little bit is like this law. If you don't do it now, then you do it late. You must do it later and pay more. Biopharma has been the last industrial sector in using mathematical model. And now they are willing to do it. They're very happy with it. They're doing a lot. And immediately now they're faced to use machine learning techniques. So hybrid modeling, combining statistical tools with mechanistic models. And they have to do it because things are happening in that area very, very fast. And those who don't do it will remain behind and pay much more in terms of time and cost their development. In academia, also, that is difficult. Different people I would say that a lot of young people, and I see that they are doing this with certain backgrounds, but I've seen this is happening. A lot of computer scientists are learning biology, learning engineering to be able to contribute in those areas. And that is probably the right way to do it. But there is a lot of knowledge needed, a lot of study.
Wow, it's been an amazing conversation, and we somehow need to land the plane now. What I usually do at the end is I ask you to provide one key or insight of our conversation. But since you're looking back on such a long career, I want to do it a bit differently today, because I would be curious, Massimo, what advice would you give a young scientist in their 20s to succeed in bioprocessing, given your extensive experience?
You see, science proceed in steps. Somebody says in jumps. These jumps are sometimes in depth, so you have to go deep on a subject and then find something new. And sometimes instead not in depth, but in being interdisciplinary. The place where we are today in bioprocessing is more in the moment where we need interdisciplinary. So maybe 20 years ago, focusing on developing a process for chromatography of maps using protein A chromatography in a continuous fashion and finding the way that you can extract three streams instead of only two with respect to the Cairo SND. That was a very deep study that required expert people, which was what we did. But today, I think that there are lots of, and the same was for the sensors, for PAT, for mathematical modeling, for the machine learning techniques. Now I think that there is a lot of things ready to be used. The problem is that the people does not know it. So I would suggest to a young scientist to try to stay on top of the bioprocessing, understanding what is needed, what are the problems that the industry needs to solve, and then understand everything which is around in terms of mathematical modeling, different processes, continuous, non-continuous, PATs, and the value today can come from the selection of the right sensor or develop a soft sensor based on some spectroscopic sensor connected to mathematical model using Kalman filters, for example, to combine model and experimental results. So this is, I think, where today my suggestion would be, which is, of course, since I'm very young, this is what I'm trying to do, right?
Well, thank you very much, Massimo, for this $1 million advice, which is so precious to all the young and not so young scientists anymore. Where can people connect with you, Massimo?
Well, I'm still using my emails at the Politecnico di Milano or at ETH. So I have one also in Thessaloniki now, but I'm not using that very much. So I always have massimo.morbidelli and then at, and then you can either go with ETH, which is chem.ethz.ch or polimi.it for the Politecnico di Milano.
Fantastic. I'm going to leave these links in the show note. And thank you very much, Massimo, for coming on the Smart Biotech Scientist podcast. It has been a true honor. And thank you so much for sharing your extensive expertise with us.
Thank you, David. It was great to meet you again at the DataHow Symposium back at the beginning of the summer. And I see that you are doing very well, in great shape and full of enthusiasm. So thank you for this conversation, which I enjoyed very much.
All right, smart scientists. That's all for today on the Smart Biotech Scientist podcast. Thank you for tuning in and joining us on your journey to bioprocess mastery. If you enjoyed this episode, please leave a review on Apple Podcasts or your favorite podcast platform. By doing so, we can empower more scientists like you. For additional bioprocessing tips, visit us at smartbiotechscientist.com. Stay tuned for more inspiring biotech insights in our next episode. Until then, let's continue to smarten up biotech.